Welcome to Integrated Math 3. On this episode, Stevenson will demonstrate
Here's an example of a polynomial function. Now, this looks kind of crazy when you think about it. This doesn't look like something we've seen before, but it does have some resemblance of some things we've seen before. But regardless, we can actually analyze this. So the first thing we're going to do is we're actually going to go ahead and do a sketch of it on our left here, just so we have a record of it. Notice I don't have any points added on here. We're going to get to that. So we're going to go through this and we're going to analyze the characteristics of this polynomial function. Let's start by domain. The domain for any polynomial function is always all real numbers. Next, let's look at range. Now, in this particular case, we can see this graph right down here has a low point, and that low value is negative 15.249. So that is its minimum. So that's the lowest point for my range. Now, what is the highest point? Well, if I zoom out, we can see it continues to grow in a positive infinity direction. Therefore, it will go to positive infinity. Next, let's look at intercepts. If we look at our graph here, we can see there's actually 1, 2, 3 x-intercepts. So if you want, you can actually identify those in your picture here. Next, let's look at the y-intercept. In my graph here, I can see it is 0,96. Next, let's find something new, something called the extrema. The extrema are the high and low points of your function. Not every function has them, but in this particular case, ours does. So let's start with the relative extremas. So the relative extrema, specifically, let's start with the relative maximum. So the relative max means what is a maximum point in our value in this particular area. So this point right here would be considered a relative maximum because in this general area around the point, it's the highest value, it's the highest location. What is the relative maximum? The relative maximum is 110.663. When does it happen? It happens when x is 0.705. Now, are there any other relative maximums? Are there any other high points that could exist here? And the answer is no. Let's look at the relative minimum now. So, just like the relative max, the relative minimum is a low point in a general area. So we can see we have two of them down here. So let's look at this point. This point right down here is the low point in this area. So it's negative 2, 0. And we have another relative minimum here. We could say there is a relative minimum of 0 when x equals negative 2. We could also say there is a relative minimum of negative 15.249 when x equals 3.545. Now, that's it for the relative extrema. So now let's look at the absolute extremas. So the absolute maximum is the absolute highest point in the entire graph. Well, look at this graph. Look at the end behavior. There's no way this thing's having an absolute maximum. It's gonna go forever in that positive infinity direction on the y-axis. So there are no absolute maximums. We just write none. Now let's look at the absolute minimum. Is there an absolute lowest point down here? Well, yeah, it is. It's right here. Now you may be thinking, but Stevenson, that's also a relative minimum. And you're right. Absolute extremas can also be relative extremas. Okay, because of their definition. However, a relative extrema doesn't guarantee it's an absolute. For example, negative 2.0 is a relative minimum. See on our graph here? But does that mean it's the absolute minimum? No, it's not, because there's another point that's actually lower than it. 3.545 is this at this point here is a relative minimum, but it's also the lowest point in the entire graph, so it also makes it an absolute. The same true is on the maximums. Let's look at those. The relative maximum is this point up here. So in this local area, it is a maximum value. It's a high point. However, is it the absolute highest in the entire graph? No, there is none. So again, just to reiterate, an absolute extrema is automatically relative. However, a relative extrema is not necessarily absolute. Now that we have our extrema in place, let's look at behaviors of increasing and decreasing. Increasing. So this graph, this function actually decreases first and then increases and then decreases again and then increases again. So let's start with the decreasing because that's happening first. So when does it start? It starts from negative infinity over here and it keeps going until, what's that x coordinate? -2. Remember, that was one of our minimums here, right? And then it starts to increase again, so that doesn't work. And then it stops, and then from 0.705 until this point right here, 3.545. So we actually have two intervals of decreasing. So what we can do to bring them together is we put this capital U, it's called the union. So we're saying this interval and this interval together are when it is decreasing. If there's only one interval present, like in our previous problems we've done, you don't put the U, but because we have more than one, we put the U between them. So let's look at increasing. So it increases here on this interval. So when does that interval start? It starts at -2, comma, and it goes until the relative maximum, which is 0.705. And then it decreases, and then right here, it increases again. When does that start at? It starts at 3.545 and continues off to positive infinity. So because there's two unions, we're going to put a U here. There's two intervals. Last but not least, let's look at end behavior. So as x approaches positive infinity, so that's the right side here, the x-axis right here. What does our y values approach? That's up here. We can see it's going to be positive infinity. As x approaches negative infinity, so that's the other side over here, what is the y values approaching? Also positive infinity.